about theorem 8 and theorem 9, if you want to look further, more detail, you can consider one-sided limit or even a one-sided continuity. For example, if the function g has a limit from the left at a, for example, here, from the left, but the values of g on these numbers are greater than L, or pretty close to L, very, extremely close to L, then we can make a more fine condition. F is continuous at L from the right, okay, from the right. Then we still have this conclusion. Whereas if when x approaches a from the left, the value of g on those points is are always less than L, but pretty close to L. Then in this case, we can replace continuous at A by a continuous from the left at L. Okay, at L. So all of this, if you realize the spirit of those theorems, you can consider by yourself some more fine statements, okay, more fine statements or weaker conditions to obtain some statements. Okay. So number 8 theorem and number 9 theorem are talking about functions essentially continued at some point. For example, limit exists at A. F is continuity at L. Continuous at some point A, continuous at some point G of A. The next theorem is about continuity on some intervals. The most important interval is continuity plus finite closed interval. Finite closed interval. There are two main results, but this author who considers the scale of this section, so he only states one of the two main theorems, and another one is postponed to next chapter when we consider the maximum or minimum values of a given function. Okay, so here, number 10 theorem has a name called the intermediate value theorem. Intermediate value theorem. The conditions is maybe only one condition. When f is continuous, on some closed interval maybe. So this is a finite closed interval. A finite closed interval. Then the conclusion is f has a maximum. The values of f has the largest one and also Oh, wait a minute. This is not the intermediate value theorem. Let me see, use what later. Oh, N, capital N. N is a real number. The number capital N between f of A and f of B. Between. So there are two possibilities. One, if f of A is smaller than f of B, and n between f of A and f of B is exactly this relation. If f of A is larger, is greater than f of B, then n between these two numbers, oh, so the second condition is n between f of A or f of B. You can use this phrase, n between f of A or f of B. If f of A is smaller than f of B, this is exactly this expression. And if f of A is greater than f of B, then this statement is exactly this expression. Okay. Then we call n is an intermediate value of this function. N must be a value of the function f as some number c, and the c is between A and B. Or use set notations from set theory for some C in the open interval AB. Okay, this is called intermediate value theorem. The geometric interpretation, or you can realize this by this graph. Okay, here we have a closed interval, A and B. A and B. F is continuous on this interval, so F is defined at A. The graph of F has a value at A, means there is a point. The graph of the function F also. So this is f of A, and this is f of B. If n between f of A and f of B may be here, okay, use this condition. F is continuous on the closed interval AB, and we can maybe draw a picture. A curve, continuous curve from here to here, from left to the right, maybe up and down, maybe up and okay, up and down, F here. Or sometimes just a straight line. Anyway, see, if we consider this horizontal line, whose equation is y equals n. This horizontal line intersects the curve of the graph of the function at least once. For example, this is C1, C2, C3. This is the meaning of intermediate value theorem. Okay. The conditions are continuity on closed interval, finite closed interval, and n is an intermediate value. Then n must be a value of this function. A special case of this theorem, when the capital N is 0, according to this theorem, there must be some number C between A and B such that f of C equals 0. Okay. Geometrically, now A here, B here. F of A may be less than 0. F of B may be greater than 0 here. Then according to the continuity of the function f, then the graph of the function f must intersect this axis at some position, maybe more than one position. Because we have an equal sign here, this means the equation. Okay, this expression has an unknown variable, so this is an equation, has a root in this interval AB. Okay. So intermediate value theorem, and the main power is to testing roots. Is testing roots. Negative, positive, then under this condition, this function has a solution, and the solution must inside or interior to this interval. C cannot here, because a function for a given number A, there is only one number corresponds to this number A. F of A already less than 0, so f of A cannot be 0, so C cannot be the number 8. Similarly, C are different from the number B. Therefore, C must be interior to this interval. Okay. So we use the open interval, or we use strict order. Strict. Got it? This means f is continuous on the closed interval AB. And the value of f at A is negative, and the value of f at B is positive. So 0 is value which is intermediate between these two numbers. So 0 is an intermediate value. According to that theorem, or intuitively, less than 0, greater than 0. So must be some place here whose value equals 0. Equals 0. This is exactly this statement. And f of c equals 0 for some number c between a and b means, this equation has a solution. What? C. X equals C is a solution of this equation. And also tells us C is inside this closed interval, means C is in the open interval AB. 好，这个叫做连续函数的中间值定理，也称为介值定理，介于两数之间。一个函数 f 如果在地区间 AB 上连续 ，n 是一个介于 fa 跟 fb 之间的数，那么 n 一定会是 f 在 AB 中间某一个数的函数值，对啊 n 呢？那如果 n 是0的时候，就会发现，在这个连续的条件之下，如果这两个端点，一个值比0小，一个值比0大，那么中间一定会找到某个数，它的值恰好就是0，因为0就是介值嘛，就中间值，这叫中间值定理。Well, so I think the content of the theory part of this section already introduced completely. Next, we will solve some examples. Do you have any? Yes. Yes, theorem.
Does that mean n is the number that
Between f of a and f of b.
yes, it doesn't mean n is the number that has the most number of antecedents?
And it can be anywhere in of this open interval.
Yeah, in this case, it has 3.
3 C's, yes. But this theorem tells us at least one for some, means at least one existence exists. There always exists a number C between A and B, such that f of C equals capital N. Okay. Yes, yes. So sometimes we use this terminology means existence. This is used very few words to describe. Or, of course, you can express this by there is or there exists a number C or at least a number C which is between A and B. Such that f at C, the value of f at number C equals n. Okay. Or sometimes we can omit there exists a number C, or just like this for some C, f C equals n for some C, the same. All of the statements are same, have the same meaning. Very good. So in the beginning, sometimes some terminologies, yes, some usage in mathematics may be somewhat different from the usage in our daily time. 所以说，有某一个就代表很严谨的存在性。For all 那更不得了，每一个都要对，那就说全称。So sometimes for some means existence. For all means this is a universal. usage. And for some means the existence usage. Example 1. In this figure shows the graph of a function f, at which numbers is continuous y. Here, f is discontinuous at 1. Why? Because f1 is undefined. Also discontinuous at the number of 3, because here the limit of the function does not exist. And 5. Why? The limit of the function at 5 exists. The value of the function at 5 is defined, but they are different. Continuous at some point A means the limit of the function at that point equals the value of the function f at that point. Okay. And this discontinuity is removable. Discontinuity because the limit of this function at 1 exists. And this discontinuity is jump. Discontinuity because one side of the limits exists. But they are different. So there is a jump discontinuity at the number 3. And at 5, also a removable. Discontinuity. Because this one exists. So f has a limit at 5. Okay, then continues at every other numbers, all other numbers. Example 2, where are each of the following functions discontinuous? For this function, the f is continuous at the number 2. Because this is a rational function, we can evaluate the limit of this function by direct substitution. So it is continuous everywhere except at 2, because the number 2 will make the denominator 0. Okay, for this function. In fact, we can simplify this one. When x equals 2, 4 minus 2 minus 2 is 0. Then the numerator has a factor x minus 2. And this one is not equal to x plus 1. Because this function is defined at the number 2, but this function is undefined. It's not defined at 2. So we have to add this condition. And therefore, the graph of this function is a straight line with slope 1, and whose y-intercept is 1. This is the function here. Okay, for this function, the same expression. But at 2, the value is 1. At 2, this is 3.